Начата запись встречи.
And after a short break, we continue. What I left here in front of you is the screen. I left on purpose this classification we did in previous class. Oh, I forgot to mention it's class number 9. Class number 9, no, lecture number 9 actually. And subject of our consideration is propulsion system of airplane, of aircraft at all, and propulsion system and power plant and engines in particular. Mostly we're talking about engines, of course, but do remember they are not the only element, the very important element of propulsion system of the aircraft, but not the only. Now, once again, while we're talking about different engines, what they looks inside and how it's work, in order to understand their limitations above the all, because design of engine, it's how to design engine, how to compose engine at all. It's not our matter. It's matter of those engineers who work with engines. It's another major, let's say, actually, or at least it's very different specialization with respect to our specializations. But we are selecting, pointing out the engine and not even particular engine, like a particular piece of bread in the shop, but type of engine at least supposed to be chosen by you first, and next of course it's some individual engine out of this type. No, in case you are designer of this airplane. Well, let's continue. We already do remember that gas turbine engines, they are similar, but anyway, even in the group of gas turbine engines, we see differences. And the first two, quite clear. They will be visually different. Turboprop, turboshaft, because they are joined, their shafts joined immediately to the prop. No, not quite immediately, via reducers. In next time, photos and schemes, we will better see it, I hope. If if I do not lose those schemes, I'm already got tired to collect beautiful pictures for you for illustrations, and decided some of them live where I see these beautiful pictures. I hope we will find it back. Not like with polars. And another three. Look, turbojet with afterburner and turbofan. All of these engines, they have generally similar so-called core as we see it on the picture on the left. And this core consists of intake, area of intake. No, it's not given in this picture with special name. Compressor. Function of compressor is to compress air, to suck it inside and to compress it. Combustion chamber, turbine, and exhaust. And what is function of combustion chamber? It's quite clear because it's necessary to combust to burn the fuel. No? And this combustion process next it's resulted in significant increase in temperature, pressure, and so on, and passing through the turbine. Actually, this mixture it's lose some energy. Turbine still portion of kinetic energy of this air and transfer it into mechanical energy of rotation. Seems like it's stealing, it's taking out the portion of energy. But without turbine, this engine will not work. I remind you how it's working actually due to what? In order to continue process once it was ignited at the beginning of process, in order to have this continuous process, not cyclic like it was in reciprocating engine on the same name of piston engine. There was cycling ignition, cycling burning. Here we have continuous burning. To support this continuous burning, you need to supply a new portion of sucked air. To fulfill this burning efficiently, air should be at high pressure, compressed air. In this case, it's something like explosion in this place, and next it's resulted in very high velocity. On exit, we'd like to have high velocity above the all and of this air, and to make air goes inside of this chamber, we place here compressor. Compressor is like pulling, sucking air inside and pressurize it, make it more compact, compress it. And compressor need rotates to fulfill this job. Let's not use word work because it has another mechanical meaning now for us. And to fulfill the labor of compressing the air, it has to rotate. How to rotate it? Seems like it's auto-rotating inside the engine due to the turbine. Hot air passes through the turbine. Turbine rotates because of this, taking a portion of energy together with air, together with turbine rotates. It's placed, like it's called, at the same spool you see right now. Combination of compressor and turbine immediately on the same shaft mechanically. And compressed air turbine rotates the compressor, and compressor supply new portion of air. What is after turbine, and why we how we transfer this kinetic energy of air into high pressure into high velocity. This is also interesting story. Let me to show you picture that it's much fun here, but oh, sorry, not successfully touched. But it's explain very well what happened inside the engine and what I need you next no, to pay attention for. Here is doesn't matter what is exactly given in this picture, what it's about, but this picture, what top picture show very well show geometry of engine in general. Here we have what at the place of intake and at the place of compressor we have, it's called confuser, the shape which reduce the cross section inside of engine. uh, no, it's reduced cross section, and due to this air passing through this place is losing velocity and no increased static pressure, yes, but here is like the bottleneck, and this bottleneck it's immediately in front of combustion chamber. In this place, no, at the place of combustion chamber, let it be throat, no, in this picture. After this throat and additional energy of fuel, which is chemically transferred no, into kinetic energy of air next. And after this, air goes into so-called diffuser. In diffuser will be reducing of static pressure in contrary and speedizing, increasing the velocity of this airflow. That is the changing of parameters inside of no, it's not inside of all the engine. It's only this place, it's only about one element of engine. It was about turbine in the book or in the source where I took it, but I just show you how it's in general looks inside this inner duct of any gas turbine engine. Let me to show you all those engines practically at the same picture now we see. What do we see here? No, really, it's not quite no, not quite like this, that probe of this engine and size of this engine so little. Maybe they did it for like for beautiful picture, let's say. In real, the engine itself will be much less, but the probe will be much greater here. No, anyway, whatever, it's visible that prop is much greater in diameter than fan in turbofan engine. And do pay attention in cross sections of all the engines. What we have seen practically some seconds ago, that one, this picture. Now you see it like reproduce it in cross sections of engines. What at this place, at the end of engine, seems like it does not correspond. What did I said? It's seems like it's reducing in cross section. But do pay attention. There is so-called central body inside, and this central body create duct, create channel which near this cross section it's much more narrow. If you compare it somewhere here, you will see that it's became greater and greater, this so it's really diffuser here inside. And in any engine actually we see the same story, let's say, like confuser stabilizing something like throat, and next diffuser which should increase velocity. And the only task for us now is to understand, how it's work, why people torture themselves with improving of those engines, why it's so necessary. uh, Here I will leave the same site with some simulators. Next we'll try to use it. Right now we try to close using talk first. Right now we will try to see something and try to understand my explanation. I hope I'll be successful. uh, oi, I lost. What do I need? Oh, have prepared. Okay, what there is gas turbine engine, and general core of it we already understand, I hope, and combustion chamber. Let me just show you some pictures of compressor and of turbine and combustion chamber in real. Let's try to see, uh, not in beautiful schemes, but in real. I lost it. I lost it. I lost it. We will find it. No problem. Mhm. Almost found. Almost found. Відчепиться. Now we see it's collection of photos, and these photos are proposed to be bought, let's say. You see real engines, something similar that we might see in our laboratories with engines, actually. Laboratories that our students may use for practical classes. uh, Compressor, and next is some empty place that looks like cylindrical bodies here. Pay attention. That is so-called can type of combustion chamber. What it looks like, it was visible here. Wait, disappeared. I meant to increase, and what I did instead, I spoiled everything. Here is. Uh, will not risk any longer to increase it. Look at this compressor. Next, you see throat now immediately before combustion chamber, and separate bodies, like separate capsula cans, so-called this can type of combustion chamber. And next, exhaust of combustion chamber pass to the turbine, no, and central body. What it looks like, it was somewhere. What here is. Would you be so kind, please, to show? No, no, have understood. Not much interesting actually for me. I've seen. I have video, and I'm going to send it to you. Video about turbofan engine. No, at least here it's visible that engine is all surrounded with additional systems, with pipes, with electrical systems, and so on. Uh, let's close this and let's go into explanation. I even tried to do it. I'm training to do it before the class, in order it looks more beautiful. Let's say. Well, once again, we have engine to make. No, we need engine, and in this engine, somewhere in housing, we are going to. What here is the housing element. And inside the housing element, we need to have first the confuser and next diffuser. So usually it looks like, and next is this housing element. And let's place it here. Somewhere here, it will be combustion chamber. We do remember. So somewhere here, it will be fuel nozzles. Some of them. Combustion chamber might be of can type, it's most typical, but also it's maybe the common combustion chamber, like the whole ring around the axis, around the spool of turbine engine, gas turbine engine, and compressor. No, look, compressor looks like approximately. Uh, compressor looks like by the words. Compressor looks like. We have seen it here in photo. There are two different popular decisions. Both are popular. They have their differences, no, like advantages, disadvantages. Not the matter right now, but do remember that compressor may be so-called axial compressor through the axis. Air pass like along the axis, no, not quite of course, but almost. And one more type of compressor is centrifugal compressor, looks like this. Turbines usually looks like normal, no, what it looks like actually. There you see it's the each that is so-called multi-stage compressor. Each stage consists of disc, and this disc is stuffed with blades. No, now they are in radial directions. In centrifugal, actually, those ribs, let's say, they are also have the blade-like shape, and this blade-like shape additionally twisted along to create complex ducts here. That one and that one, they are both placed in confuser area, in confuser area. Either or. I've seen engines where it was hybrid. It means one portion of compressor was made of as axial compressor and another one like centrifugal. Whatsoever, I will draw schematically. Axial compressor, not so important which one. And I'll draw it even of maybe blue color to emphasize that this thing is yet cold comparatively to the temperature in combustion chamber. And I made now one stage of compressor here. Next, I'll do here one stage of turbine, for instance, somewhere here. Let it be turbine here. Turbine is necessary to rotate compressor, we do remember. So everything is necessary, everything is in common shaft. And due to rotating, no, some at some moment it was necessary. I draw only the half, you understand. It's necessary to start rotation. Rotation have started, engine is socket, and next it's like out of work, on continuous cycle of burning. How to increase the thrust in such an engine? How to make it like more efficient, more powerful, more capable? Maybe we need to give more fuel. We may give more fuel, but to no, this trick will work in case you have more air. So first we need more air. How we may get more air? One way is to increase engine dramatically, and this engine, of course, will be not already for airplane at all. What is another way? No, quite obvious way is to increase amount of these stages of this disc with blades. Okay, let's do it. And even more, I still haven't drawn it, but it has compressor has so-called rotor and stator. Inside of this, between of these blades, there are, no, maybe I draw them not conveniently for this explanation. There are also blades, so-called stator blades. Altogether, they create very complex channel, very complex duct, and make air to squeeze through this duct, and it's compressed efficiently. So to increase the possible efficiency of engine, possible thrust, we need to increase amount of these stages of compressor. We need to increase compressor in order to increase air compression ratio. I hope you understand it intuitively. What does it mean? Uh, okay, we did it. No, quite clear that to rotate more heavier compressor, we need here more capable, more powerful turbine. Also have increased. No, and similar matter is with turbine. It also has additional blades here. No, it's like ducted in special channel usually. In order, it's in order. I might even show you what it looks like. I place it here. No. And you see, no, there are different types of turbine blades, but mostly it's look like, no, you see what rotor of turbine now. Mostly they look like typical, what quite typical airfoils directed in the direction of flow, let's say. But in contrary to compressor, which not so similar to this blade, it's also blades also, but they are not so similar. And I even left here the picture. Oh, here is turbine blade. What it looks like. It's very complex structure with inner holes for cooling. Why it's need holes for cooling? Because it's subjected to the dreadful temperatures actually. How it's not melted at all in the engine, and it's like no, it's one cross section we might see with channels for cooling the blade. It's like little piece of it, and additional what little piece not far from this place you see, and additionally this profile, this airfoil along the lens, both in compressor and in turbine, they are twisted. It's so-called aerodynamical twisting. So angle of attack is changed along along this span, let's say, of the blade, along the length of the blade. By the word, it's similar matter to propeller prop, which is in front of turboprop engine. It's also looks like aerodynamical airfoil, each blade of it, and this aerodynamical airfoil, it's twisted along the length of the blade. Oh, do forgive me. Do come back again to engines. Так, and we are, no, let it be here, this picture yet. And No, at the some moment, quite clear that pressure here, how to increase, we are trying to increase capability, as I said, no? And we are trying to increase the capacity, the power of this thing by simple mechanical increasing of parameters here. But everything has limits, starting with the fact that the pressure here might be such big that we already not able no, structural materials, they are not able to withstand to this pressure, for instance. Or temperature will be so high that turbine will be just melted in this place, and so on. So there are some physical limits, and seems like it's not possible to change situation by increasing the like intensifying the engine inside by increasing the stages, and you have to increase thrust, you have to increase sizes, cross-sectional sizes of engine. Is there any another possible way to increase the capacity of engine in this case? What people understood with some time. No, one decision was maybe we burn not with we may compress, we may suck more air than necessary at this place, and burn partially the most of air, the most of oxygen in air will be burned, will be used here in this combustion chamber, and some portion of air yet containing the oxygen may be additionally burned in another place, in afterburner, after the turbine already. Sorry, here. And this is resulted in appearing of afterburner chamber in engine. Where it was. So turbojet engine and turbojet engine with afterburner, they are very similar. Just afterburner, it's additional combustion chamber at the end. And what it resulted in? Of course, it's resulted in increasing the thrust practically with the same sizes of engine and with the same amount of inner elements of engine, no, practically, but engine became much longer. But what happened to fuel consumption in this case? Of course, it significantly increased fuel consumption. Is it good decision for cargo and passenger airplanes? Certainly not, because in contrary, they are trying to save money for each flight, to save fuel and to save money. And last 30 or 40 years, it also became very important about the due to this sustainability approach, and due to the considerations about environmental matters, to save environment, to have no to not to make damage neither to people nor to the nature, and so on. Так, and I forgot to draw here, should be so-called central body. Pay attention that central body or things that correspond to like this intake channel, I draw it automatically like subsonic engine. And in case of higher speed, we use more thin profiles, more sharp profiles here. Well, so it's not the way for the passenger aircraft and cargo aircraft. What we really wish to have, once again, we need here velocity, high velocity. how to increase the thrust of engine. One way to increase velocity, and another way, extensive way, seems like, to increase amount of air of this velocity. Somehow to increase amount of air that pass through the engine. It's not compulsory necessary to burn this air. We just like to speederize, to accelerate this air somewhere in the engine and push it out. And what people did understanding this, let's copy down this thing. Wait a second. I hope I do it. Oh, I did. In order to place here additional element. And what this additional element is. In front of compressor, let's place, yes, you do remember we may use props. I already said it, prop is efficient only up to some speed. And up to some speed, up to some altitude. Just because of mechanical matters, this mechanical strength matter. If speed of rotation, how to increase? Once again, problem is that 70% of thrust created due to rotation of prop in such engine, turboprop engine. And to increase thrust, you need to increase either size of this prop or rotation per minute of this prop. No, in order it's give more air and another speed of this air. Increasing size of the prop. No, I'm already said you need to compare the size with the size of your airplane. Maybe a prop will be too big. Increasing speed of rotation of air prop. It's maybe mechanically broken due to rotations. At all, you should understand that I said it, but maybe not clearly, that between the turboprop engine itself and the prop in front of this engine, you have so-called reducer gearbox, which reduce rotation of turbo engine shaft in order it's rotate the prop with less amount rotation per minute because rotating with the same speed as engine itself, prop will be destroyed in some seconds. And also rotating prop faster give more rotations per minute. It's also not a decision. So if we try to increase capacity of turboprop engine, we have limit either of its diameter of this prop diameter, or we have limited with amount of rotations per minute. Not just because I said mechanical strength responsible, let's say, for this limitation. But what was noticed by those who studied aerodynamics, scientists who study phenomena of aerodynamics, of different ducts, of hydrodynamics, that the same probe placed into channel, into duct, give more efficient result. Why? No, because of additional effects of those confusers, diffusers of different shapes. And what it was proposed to do. In front, let's come back to this picture, in front of a compressor, let's place something, no, okay, like this, little. Let's place additionally one more device, so-called fan, and it has already the only stage. There are no some stage necessary. This fan, it's shorter in diameter than it was turboprop. It also looks like a prop, but this prop is more similar, no, more similar to the turbine, more similar to compressor. It has a big amount of blades. Blades are shorter and they are hidden in the special channel. Let's do here something like beginning of the engine, and they are hidden in additional channel. And this channel also it's profiled no, with respect to that rule that first we need a так, I will not try to draw it beautiful. I will just stop drawing at some moment, okay? Так. And here is we have, as I said you, no, seems like additional housing with respect to the turbojet engine that looks like this. Here we have added additional element in front of compressor. Its element name fan, and fan also rotates together with compressor. It rotates with the same rotational speed as the shaft itself. No gears, no any intermediate devices between them. It just rotates, and rotating of this big fan resulted in passing air in two ways actually. Portion of air still goes through inner duct of engine like this here, but some another portion goes through the outer duct here, which is also profiled for the purposes of first uh, compressing, no, not compressing air, for the purposes that air velocity at the exit will be higher than air velocity on the beginning of this duct. So it's also profiled somehow. And what is resulted? No, what is the result of this? When here we had no accelerated air amount, for instance, at the top, we had accelerated air symbolically. I show it twice now here. Here we will have amount of accelerated air through the hot channel, so-called inner duct of the engine, and through the cold channel. So some portion of air make bypass, passing by the engine, not through the engine, but by the engine. That is why those engines also has another name, bypass engines. Turbofan engine in no, in literature somewhere in internet you might find it with a name bypass engines. And these bypass engines, they have very important characteristic which is called bypass ratio. What is bypass ratio? It's amount of air, no, let's show it symbolically, amount of air passing through the outer channel called, let's call it, and to amount of air which goes through the inner channel that I symbolically have shown with another, let's call it hot. Symbolically have shown it with another color. And quite clear that in this case, to create efficiency of this engine, what you need to do? You need to increase this bypass ratio somehow. It may be increased due to increasing the fan size. Yes, it's not ideal decision, let's say, because it's resulted in increasing the general size of engine, and not any airplane may may work with such engines. They are greater in size than normal turbojet engine, but they are more efficient. What does it mean? They are more efficient. Whether they give more thrust? not more thrust. No, practically like weight efficiency, it's the same like for turbojet engines, and even maybe even a bit better. Uh, I mean, amount of thrust to the engine weight, it's practically the same. But they eating less fuel. They are consuming much less fuel than normal turbojet engine, having the same thrust. And this fuel consumption ratio, we will see next it on charts, it's important exactly for for civil aircraft, for passenger and cargo aircraft, for passenger and cargo airplanes. But increasing of bypass ratio, it's resulted, of course, in increasing of overall sizes of engine. No, and plus to this, you may also work with aerodynamics of inner channel of aerodynamics of these blades, but make them more perfect, let's say, in order to increase aerodynamical characteristics of this inner duct and to have higher velocity on the exit. And of course, it's no, like not ideal decision, seems like. No, but let's try to draw here what was cold area. Now what this. So to understand this bypass ratio, it's possible to draw in the view of circles those things. But look, area which is twice bigger, no, like additional area of the same what I draw right now, I did, do forgive me, I did seems like twice bigger diameter. Okay, twice bigger diameter, let it be now visible. But this twice bigger diameter area, what in this dark area will be not twice bigger. You do remember this formula, pi d by 4, by 2, да? By 4. PD квадрат, деленное на 4. Так. Вот. And because of this increasing in, no, not much significant increasing in outer diameter of the fan, it will be resulted in significant increasing of bypass ratio. So the size of engine grows, but not so dreadfully like it was with the prop, for instance. And that one I will close. Somewhere I have prepared. What here is prepared the picture. They show schemes of real engines, and no, I understand it's still in video. We will not try to see this video. How to grab it, I'm not understand, but right now let's not spend time on this. What is visible here? Look, both engines are turbofan engines. Pay attention. It's visible. It has inner duct. What here is compressor, and some air comes through compressor to combustion chamber and to the exit. And outer duct you see here with fan. What it's so-called low bypass. Practically, this fan by size doesn't not much differ from the compressor size. And why it's called twin spool, by the word, I forgot to say. There are so-called compressor of low pressure first, and next compressor of high pressure. After each stage of compressor, pressure increase, and increase. And here is two-stage turbine also, you see. First turbine joined, mechanically joined with compressor of high pressure. It's so-called high pressure turbine. And second one is respectively inside of this shaft, inside of this spool, pass to compressor stage of low pressure compressor. And all of this is they just rotate with different speed. And here is we have mechanical joints also with the fan, and the same type of engine, but another bypass ratio, and you already see what it looks like. And do pay attention what is also visible by the word. What is intake bodies? You see what central bodies on in exhaust channel here, and they are not visible to compare. But here is visible intake central body of two engines. How do you think which one fly faster? No, which one is for faster airplanes? Your prepositions. No, beautiful. You can't answer me right now. So you understand the more sharp, more thin shapes correspond to the higher speeds. You have seen it in examples of profiles, in examples of aircraft shape. And here is more circular, no, more flat, let's say, central body on intake. It means that this engine is designed to work with less speeds of flight. Так, I hope that we don't need any longer. And let's continue this story. Now, about bypass ratio engines, I hope I explained it to you. And additionally, I'm going to send you, as I said you, short movie. This short movie seems like animation for children. It's very simple explanation, understandable, and it's not boring. In contrary to my explanation, it's not so boring. Once again, we have engine, turbojet engine. Let's take a look. Let's recognize them. Let's different engines. Here is simple turbojet engine. Oh, simple. It's simple, people. Trust me. That one is simple with actual compressor with combustion chamber next, and turbine, and no, and exhaust channel, of course. Intake, compressor, combustion chamber, turbine, exhaust. Turbofan engine. Where is it? Where it's disappeared? In cross section. Turbofan engine. No, it's not cross section, but at least we see its typical shape. No, it's like with big hand something, and thin, no, thin waist, and next some legs, for instance. Typical appearance, and in scheme here is the fan, turbofan engine. Look at this. Very well visible. Also, compressor, two stage. No, symbolically, it's shown one stage of compressor here. Да? No, two stages. Low pressure compressor given like axial compressor. Next, high pressure compressor is centrifugal compressor, and after combustion chamber, you have two stages of turbine, respectively. One is joined, inner one joined to the inner compressor, so they correspond to high pressure, and they are working with high pressure. And outer ones, both compressor and turbine, they are working with low pressures. And fan in front. And you see symbolically it's given that air pass partially through the inner portion, and it's hot, and partially through the cold channel, no, comparatively cold channel, and of course it's cold at the exhaust channel. And I should also add, maybe it's not important, that different designs of engines may be in the exhaust chamber, in terms that air, cold air and hot air may be like joining together, or in contrary, they may go completely separately. And what is better, what is worse for different speeds, it's another story. Uh, next, That one I hope we somehow understand now. Difference in principal difference in their design. Next, what I propose you to take a look onto. At the top, what is it at the top? No, once again, if I open, not if, but when I open the picture, this picture we've seen already. Do take a look, like scheme of inner duct of engine. And once again, what here is symbolically visible. Inner duct, first we have confuser, next diffuser, no, some stages of diffuser, and air goes out passing through this core of engine, so call it, no, it's rotating core, and watching the real photos and schemes of real engines, we understand it's extremely heavy thing actually, and to rotate it, it's not simple task. It spent a lot of energy, a lot of kinetic energy to rotate these inner guts of these engines, let's say. May we work with these shapes of inner ducts in such a way that air first compress, next we add the fuel, of course, in order to increase the energy of flow, and next it's diffused outside, expelled, expanded and expelled outside. May it's possible? Yes, such engines exist. Look, uh, it's so-called RAM and scram engine. What here is, look, it's empty inside, completely empty. Here is device. It's unmanned flying vehicle made in USA, Lockheed for reconnaissance, purposed for reconnaissance. It's 60 years of previous century. And look at the engine that this thing seems like it's using. Engine simple and empty inside. It just profiled duct inside. Some central body, you see it's sharp, it's for supersonic speeds. Um, Here is a combustion chamber, and next it's just exhaust channel. No problem. Great engine, very simple. Seems like very weight effective because it's certainly it will have less weight than gas turbine engine, heavy one. The only problem is how to make air to compress, how to make air to squeeze through this place, how to force it to squeeze to this place. In order to start work, this engine already, no, this aircraft with this engine, first it should be speederized up to the very high velocities, better supersonic. So it may work, yes, but to start it work, it's starting it from Mach button 2, 3, not at the beginning. It's not possible to start, like with the takeoff of the airplane when you have no velocity yet. It doesn't work in this at this at this moment. And yes, such engine may be used, but it means that first you need to accelerate your aircraft, your airplane, or whatsoever you have. First, you need to accelerate it and to very high speed. And it means that it comes again about hybrid power plant. Seems like, no, I'm already said you, the English literature describes those engines like RAM engine and scram engine because they have differences in inner design of those ducts, let's say, and they are used for different ranges of speeds. But in our language, they are called, no, if I use direct translation, it will be like straight flow engines, engines of straight flow. No, like this. They are not in the group of gas turbine engines, we understood it, but they are in the group of jet engines anyway. They are for supersonic, beta, hypersonic speeds, and they are start working already on only on supersonic speeds. In order to use such engines in aircraft, whatever aircraft is, first it's necessary to accelerate aircraft somehow up to the supersonic speeds. More probably, in this case, it's used hybrid power plant. Actually, we even have example of such airplane. Also, it was reconnaissance airplane of USA. Черный дрозд. Wait a second. That one. Blackbird. Lockheed, Blackbird. No, I trust you may find it in internet or movies about it or some information about it. Look what it looks like. Very interesting shapes. Certainly purposed for supersonic flight. And that one, it has such type of engines. There are two engines of this type, but they start work only after airplane get already necessary velocity, supersonic flight. And it has additionally a lot of problems during subsonic flight, during the uh, in position on the airfield, they permanently have problems with this engine. So this airplane is a very interesting example, but it's not in service, let's say, uh, really. It was in service, but not in service right now. Well, it was about engine types. I hope I practically haven't missed anything. Let me to check what I'd like to say you. No, seems like not. A lot of these beautiful pictures, as I said, everything is great. Internet is full of those pictures, and you may use it for your own. And I need you to have like strong understanding in your heads that all those engines they are different. Yes, design is different, principle of operating may be different, but what they are different for us with? They are different with characteristics like amount of thrust to the weight of this engine. Uh, First, like a relative thrust relative to the weight of engine. Quite clear that we'd like to have more thrust with the same weight of engine, for more efficient airplane. And it means that this relative thrust should be higher values. This dimensionless value should be higher. No, it's not quite dimensionless. No, doesn't matter. If you compare two engines, compare it's like thrust to the weight, which one is better? No, theoretically at least, where this ratio is higher. And one more important characteristic, not quite clear that this characteristic at the first point, because it's a rule for any airplane, this minimum of mass weight efficiency. And next consideration is the fuel consumption, of course. When this consideration work, when it's important, for instance, for military aircraft, whether it's important or not, no. When it comes about military airplanes, no one counts the money at all. It's expensive. Okay, it's expensive. It's cost how much it costs. Doesn't matter. If someone ready to pay for this, of course. But when it comes about passenger aircraft, cargo aircraft, it's your money. You spend this money, and of course, you don't like to spend more. And in this case, we need to see. No, we might to see some pictures right now. It's about limitations of engines. That one. Fuel consumption. And I will draw for you. I will just draw for you some things. I didn't find them exactly in the way that I get used to in our books, in our language. So I will draw it. I took it from different places, and on one hand, no, there are two sorts of pictures here. On one hand, it's about limitations, about area of using of engines, and on other hand, it's about fuel consumption. What that one, it's about fuel consumption. What thrust specific fuel consumption. You see English abbreviation TSFC, thrust specific fuel consumption. What does it mean specific? It means that it comes about amount of fuel to amount of thrust produced by the engine. It may be given in different units. In our country, usually it's in so-called metric units in international standard. In some countries, it's given in pounds, in horsepowers. By the word, traditionally piston engines, even now, compulsory given their thrust is given in horsepowers. No, actually, all the engines in brackets they have this horsepowers equivalent. They have it in force, like in newtons, and also they have it in horsepowers traditionally. And let's see, where is it? Not this one. I had it. No, what cruise fuel consumption. Oi, cruise fuel consumption. I love this. I took it like screen from short movie about engines because it's visible where those what is the type of engine, let's say. uh, well, what we do see that engines have different fuel consumptions uh, with respect to different speed, let's say. And the worst, no, the worst are not even shown here. Look, worst are turbojets. Turbojets with afterburner will be even worse. They are not shown here in picture, but they will be even worse. Turboprops, you see, have less fuel consumption. They have more efficient, seems like, consuming of fuel. What is the reason that we do not use them everywhere? No, next you see that turbofans are next with respect to the turboprops, like they're intermediate in fuel consumption with turbojets and turboprops. And the higher bypass ratio, the closer they are to the turboprops. Quite normal bypass ratio, no, what we started from, it was 1. And 2, 3, 5, 6, it's already quite common engine. It's normal engine. You see, typical passenger modern turbofan engine is with bypass ratio not less than 6, 8. It's normal bypass ratio. Of course, they are much bigger in size that to pay attention to the turbojet and to proportion of this turbofan. Given the same thrust, they will have greater overall sizes. But they, given the same thrust, they eating much less fuel. And the most advanced, you see, with bypass ratio around 15, as you might see. They, of course, huge with respect to the normal turbojets, but they are practically the same in fuel consumption as turboprops. Let me to draw approximately the chart of this fuel consumption in the way that I get used to see it and get used to draw it to my students. Actually, usually we draw it even with values. No, sorry, not right now with values. Now it will be qualitatively. This characteristic usually is designated in our literature like this CP. It's trust specific fuel consumption in English literature. And depending on their speed, Mach number. Let it be here somewhere. Oi, Mach number 1. Let it be somewhere here. And fuel consumption of, no, as we have seen in previous picture, just stop it. Stop it. Of turboprop engine. Of course, it doesn't start with 0. It's Mach number 1 somewhere here. And it starts somewhere, but it's close like this. In transonic area, turboprop engine start growing fuel consumption, and at some moment it just doesn't work at all. When it comes about the turbojet engines, they behave in different way. Their fuel consumption is much greater. Let it be, no, let it be this one, for instance, color. It started originally, since beginning, it started somewhere here already, comparatively to that turboprop engine. And it's practically stabilized, no, like this. It's not ideally correct curve right now, I draw. Practically it's stabilized, and next it's practically the same in cruise speed. Not ideally parallel to this line, no, something like this approximately. It's a turbojet engine. What about, no, okay, I will not try to type it completely. Turbojet engine. Turbojet with afterburner. It will be much higher. It will be somewhere there, not outside already. Yeah? It's turbojet with afterburner. Not quite clear because we're adding the fuel. Yes, we have more thrust, but we spend much more fuel. What about the engines with bypass ratio? They have intermediate position with respect to this turbojet. No, let's start there somewhere here. And problem is that at this place they, no, seems like they are not so effective already. They not start consuming the fuel more. They are about to stop breathing at this place. And bypass ratio 1 is rather close to turbojet engines, significantly less, but rather close. And the more bypass ratio, no, let it be 2, the closer it's to turboprop. But it still continue to work when turboprop it's already stopped its work, you see. No, let it be bypass ratio 5. The closer, the higher bypass ratio, no, the greater overall size of engine, but the closer it's to turboprop, and it's yet less in size of turboprop of the same thrust. And turboprop actually it's already stopped its work because it's not able to fly faster than 0.8, for instance. It's not able to give thrust for transonic and supersonic speed at all. Only jet engines. It has limit. Piston engines, where they are, so good, so beautiful. Steam engines, piston engines, where they are. Originally, they have much less fuel consumption than even turboprops, but they start dying approximately in the half of Mach number. No, zero point 0.5. It's around 500, no, 400 and something, like 470 kilometers per hour, and they already about to die. And fuel consumptions also rise significantly, like this. But they are already not able to breathe even at this speed. No, approximately 0.4, 0.5 of Mach number. So, how to select engine? The question is, first, we need to understand what is our cruising flight. Quite clear that at the takeoff and landing we need much more thrust, да? But there we first see where the cruise range of our airplane. Is it there somewhere along this line? What let it be? We are going to fly in this region. Do forgive me, we already limited. We have no another choice besides of turbojet and turbojet with afterburner. Next, if we're going to fly somewhere here, let's check what is more effective in this area, in this range of speeds, of velocity, of flight velocity. If we're going to fly here, what is our choice will be more probably, more obviously, our choice is piston engine as it has the minimum fuel consumption. If we're flying in this area, take a look. What is our choice? Obviously, it's turboprop engine because of minimum fuel consumption. And if we goes far, somewhere closer to transonic speed, in this case we have obvious choice, bypass ratio engine. No, turbofan engine, correctly. Well, now after understanding this, let's continue. And I forgot to mention, no, I do not show them in this area. They are not comparable with air breathing engines of gas turbine type and of piston type. RAM and scram engines, they will be somewhere in this region of flight. And for this, we are going to draw one more chart with limitations. I will show you where in slides you have similar story explained. No, that is trust specific fuel consumption here and there. It's practically the same. It's taken from two different sources, but you understand it's very similar. I hope you understand. You've noticed it. I hope. No, not quite. Sorry. This one and that one. What? Look. No? Here is visible on this chart. On this chart, I took it once again in different sources, but let me to align them together. I'll do one trick right now. Oh, did I? Once again. Great. Aha. What? Now they are aligned. No. What? Fuel consumption and fuel consumption. It's the same information, let's say, about different areas of using due to fuel consumption of turbojet engines, bypass engines, and turboprops engines. No, piston engines and some other types of engines, they are not mentioned here. Now, take a look to this diagram. It's so-called efficiency, propulsive efficiency for different configurations depending on the airspeed. Somehow it reflects the story that we have already seen when I draw it here. What? this story with limits. Let's try to understand it. Now, look, uh, again, they didn't show piston engine here. Piston engine will be approximately what somewhere here. This curve will be and fall down earlier. Here we see airspeed, and airspeed in miles per hour. It's approximately, no, I hope you do remember from previous classes, approximately 1,400 kilometers. It's 1,000 Mach number. It's thousand of sound speed, speed of sound, да? Mach number one. And no idea why it's given here Mach number one like this. Because it's in not in kilometers, in miles. Да, do forgive me. Mile is greater than kilometer. It's around 1.5 kilometer. 1.4 kilometers if it's simple mile, and 1.6 if it's so-called C mile. What they try to show here, look, turboprop, what here is turboprop efficiency, propulsive efficiency was high enough in some area and makes it sharply fall down. No, how they calculate this efficiency is just another formula to be used. It's not direct understanding like how much fuel with respect to the same thrust. No? And here is shown what is more effective in different areas. And if curve is stopped, it means that engine not able to work next properly. Do pay attention. What is the engine which able to work on Mach number out of Mach number one, no, at supersonic speed? Among these engines that mentioned here, only turbojet engine able to work with airplane of supersonic speed. You see, the low bypass engine, it's not so fuel consumption efficient, but it's able to work far, like in higher speeds than low high bypass ratio. But you see, it's consumed more fuel in turn, but it's not in another chart. And on other hand, it's able to work far on higher speeds. No, and if I try to continue the story, no, first we need to come back to one of the first pictures with diagrams. That one is so-called attitude speed diagram of different engines using. What does it mean, attitude speed? You understand, one axis is attitude of flight and another axis is speed of flight. Here is we see approximately in Mach numbers it's given. No, I'm already explaining to you. It's more convenient than recalculate different speed on different heights in order to understand what effect we're dealing with, subsonic, supersonic, and so on. And right now, let's try to draw such a diagram together, at least approximately, in order we may understand better this picture. Let's try. So we have heights, attitude, and we have Mach number. And we have formula of Zhukovsky. I hope you do remember. Cy, kinetic energy of flow, and area of wing. And the same is, but with Cx and area of middle is for the drag. Well, the height and Mach number. Now, when we have zero speed, we have no lift. It's understandable, да? And on some height, where we have no, with changing the density of air, here is the density of surrounding air, uh, air is less dense and it's not enough, no, it's not tight enough. Let's say if you fly with low speed, you have no lift in this area, let's say. Usually this curve looks like, in that picture is given in a little bit more complicated way. I'll show you right now. So higher than this curve we can't fly because just we have no lift enough. Either near the ground we may fly with low speed, no, comparatively. If we get heights, what it resulted in, with the same speed we have no enough density. So that is upper limit, and this upper limit approximately looks like this. Okay, let's fly faster. If we are limited to fly higher with low speed, let's fly faster. But as only we start flying faster, we have one more problem: aerodynamical heating, overheating of the surface. And if we fly faster in dense air, it may be resulted in the melting of our airplane. No, not literally melting, but even, you know that with changing of temperature of structural material, they change the strength reducing with increasing the temperature. It's a principal law of any material. And if airplane temperature rise, it means the strength of material reduced and airplane is not able to withstand to loads, to outer loads. So here we have limitations somewhere due to aerodynamical heating. Due to friction, due to aerodynamical heating, near the ground, it's not possible to fly with high Mach number values just because airplane no, literally melts. It's burn and melts. Great. Now we have some no, some channel, let's say, for our flights in terms of altitude and speeds, and how engines area are placed in these different places. First, yellow piston engine. No, I do not remember clearly where this beginning of this point. Something like around 1.2 Mach number. We may refer to this diagram. No, here it's one. No, let it be one. Uh, Aerodynamical friction. I mean, no, let it be even one. If it's Mach number 1 in this place, it means that piston engine area it's somewhere here. What you may use piston engines for Mach number less than 0.5, it's around 0.4. And for altitudes, well, literally 5 kilometers, not more. Take a look in the diagram. Oi, oi, oi. In the diagram here, they show this curve. No, you see, they show this curve little bit higher. No, in the literature that I get used to read and get used to use in our classes, I know that piston engines they are limited in heights and they are not able to reach 20 kilometers, for instance. So maybe I just misunderstood this chart, maybe a bit, or maybe it's a bit wrong because it was given not in textbook, it's given in internet, and what is given in internet it's not compulsory not compulsory correct, not compulsory honest, let's say. Here is purple one, turboprop engines. I hope you do remember what did I said. I said that they are able to fly approximately, no, efficiently fly approximately with speed up to 0.8, 0.7, 0.8 Mach number. So they are limited on this side, Mach number approximately 3/4 of speed of sound, and they are limited also with heights around 8 kilometers, if I'm not mistaken. So next area, it's area of turboprop engines. Jet engines, they are also limited. No, not so directly like it was uh, simple jet engines. I mean, like it was with this too. They are somewhere here. Exact values by heart do not remember. It's necessary to refer to literature. No, in our consideration right now, it's not, no, as for me, it's not important to reproduce all the values. I need you to understand qualitative picture of this problem. They are approximately here, so they may be used here. Where these turbofan engines, what they were, blue color, where they are, no, depending on bypass ratio, they are somewhere here, not, it's already overestimated, do forgive me, not exceeding Mach number. They are not purposed for supersonic speed. And high bypass ratio will be more and more and more, no, closer to the to the turboprop engines. No? So they are approximately in this area, extremely efficient, but not able to fly fast and high. Extremely efficient in fuel consumption, in economical meaning, in case we need to save money. And look what happened. Seems like this area where we have no limits by lift, by stall, and by aerodynamical heating, here is the area where we may fly. Yes, it's not reachable. It's not taken by any another engine. Actually, I forgot those RAM and scram engines. No, let's give them some crazy air, crazy color, like pink one, for instance. They, of course, are able to fly much far in speed because they are purposed for supersonic high values of supersonic flight and for the high hypersonic flight. No, okay, let it be even 5, 6 max number, even 10. But what is next? Next, air breathing are not working. Air breathing engines are not able to fly in this area. So this area is not reachable. It's not usable. It's usable, and answer is it's usable for rocket engines. Not quite clear if we agreed. We agreed. I said it and we agreed. Yes. Rocket engines. That we do not talk about rockets. So I'm not explaining much about the rocket engine now. Uh, we may use literature. Literature you will have, I'll download it today uh, together with these videos. That literature that I took on internet, once again, those books of Federal Aviation Administration, they are focused mostly for pilots, and they are purposed for pilots, not for engineers. They are not explaining like principally the differences, the reasons of this difference, and so on. They just give you, like stay you in front of the fact, let's say. stand you in front of the fact that that is like this, and do live with this. Yeah? But they also give information shortly, briefly, and illustrated richly. That is why I like it. For beginners, practically, even for beginners, engineers, practically ideal books, I would say. And there is also information about rocket engines. No, as I'm already said, you rocket engine, it does not no, it has no any communication, let's say, with the air. And rocket engine looks practically as combustion chamber. No, if I draw it here, oi, 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 I have no place now. Okay, let's get place. It's look like I draw it now in vertical position, like for space rocket. Combustion chamber, and this combustion chamber it's finished. No, you do remember already those stories about confuser, diffuser. It's finished with diffuser of specific shape, Laval nozzle, so called. And how it's work? It's need to burn fuel here. Fuel supply. Okay, we have fuel supply inside. Somehow it's injected. But to continue this chemical reaction, burning, it's necessary to have, besides of fuel, here we have fuel tank, for instance. Besides of fuel, we also need what? We need some oxidizer. Usually, oxidizer on board of rocket is already no all on board because as I already said you, it's fly with such a speed that air breathing, like sucking the air on such a speed, will be not efficient. It will be not enough air to continue burning in this engine. That is why usually oxidizer is already on board and the fuel tanks separately, oxidizer tanks separately. They supply both oxidizer and fuel into this combustion chamber, and uh, after fuel here is burned, no, let it be it's the flame or something like explosion inside. uh, this fuel goes huge pressure, quite clear, yes, and this fuel goes outside, not fuel, do forgive me. This accelerated air goes outside, and due to this shape of diffuser, it's accelerated even more. On the exit, it has very high velocity. Here it has great pressure, and here it will have high velocity. That is idea of rocket engine. And rocket engines, as I already said, they for using in area where air breathing engines not able to work at all. What rocket engine looks like, if I'm not mistaken, it's given in the book somewhere about aircraft engines. It's fly, it's about propellers, it's about, maybe I'm mistaken, maybe it's not. Because as I'm already said, those books, they are for pilots. They have more practical purpose, let's say. So to illustrate my words about rocket engines, if I already really do not remember, did I prepare it or not before? I forgot. I have prepared those simulators to you. Let me to see the time. 1945. I'm over this time again. Sorry. No, prepared to show you those simulators. No, it's, to be frank, it's nothing much interesting. Just what if we see that is so-called core of the gas turbine engine, how to work, and the only profit of those simulators that it's clearly visible the duct in this, and you may see different aspects, let's say, of flow inside: temperatures, pressures, velocities, and so on. And also we may see it for different types of engines. What that is engine with afterburner, you see. Now here is additional device which supply additional fuel, and due to this it's increase thrust producing with the no, practically with the same air compressing in the duct of this engine. Так, and no, this simulator we will not even try to use. Maybe somewhere here we might find also rocket engine. I trust it's represented here. No, rocket engine. Oi. Oh, what do I? Rocket engine. Pictures. Rocket engine. No, practically the same scheme that I draw in front of you. You see, engine itself, it's practically consists of combustion chamber. Of course, it's all surrounded with system of supplying the fuel with all the stuffs, pipes, electrical wires, control system, dreadful thing. And it's finished with the huge specific shape, what you see, of so-called Laval nozzle. And this diffuser responsible for drastic increasing the what is it? No, да, practically what real engine is given here. Да? The whole engine what consists of combustion chamber, rather little with respect to this huge diffuser which need to accelerate the air. Very well. Once again, what was all this story for about engines? Practically all the story was for these two charts. In order we might understand that different design of engine is appeared in our strive to increase thrust on one hand and to fly faster, and on other hand to save fuel in cases where it's necessary. Our strive to increase thrust and to fly faster, it's resulted, no, to increase thrust, I'm already said, you may increase sizes of engine, but it's not efficient. It's so-called extensive way in design. And intensive way is to use another principle of engine work. No, like from piston engines, people came to the jet engine. Jet engine for increasing efficiency of jet engines, people has invented not efficiency, the thrust of jet engines. People added the afterburners into these jet engines, and in our strive, that is because we are greedy people. Yes, normally we'd like to save money, we don't like to waste money, and because of our strive to save money for each kilometer of flight, we have so-called bypass ratio engines, turbofan engines. On one hand, no, like it's like a balance: the higher flight of speed, and you stand with the need to spend more fuel, even in low speed. Do pay attention once again. Even in low speed, in case your range of flight is somewhere here, even at low speed, you are wasting fuel, seems like. You need to start with high fuel consumption immediately with respect to the piston engines or turboprop engines. But if you fly with very high speed, you have no choice practically, because in contrary, neither turboprop nor more piston engine, they are not able to breathe on higher speeds. They just really disabled to do it. And additionally, turboprops are limited due to their no in piston engines. It was not so notable because they do not fly with such speed. But when it comes about higher speeds of turboprop engines, it's appeared that using of unducted probe, it's practically no, it's not even not efficient. It's practically not possible in some speeds because such a probe may be just broken or it stalled airflow on the probe and so on. So this probe is not efficient. And ducted probe in fan engines, it help no fan. It's not. I call it ducted probe, but really it's a little bit different from a typical probe. You do remember, I hope. Oh, slides where you are. Now here is a turbofan engine. Oi, better to use word. And in this case, maybe we will see simultaneously some things. What there is no turboprop here. My mistake. No turbo fan engine. Fan of turbofan engine. What here is it's visible. It's almost the prop, but prop usually have two blades, four blades, six blades. You may even place a couple of props on the same axis, one by one, for instance. They may even make direct in different sides in order to compensate this torque moment of the prop. But anyway, they are not efficient so much as the fan, no, the prop, which is limited inside of special channel, in special duct, like this one. One more name of fan, it's ducted prop, by the word in literature. And these ducted prop engines, they, on one hand, may fly with higher velocity. They have these limitations far in velocity than turboprop engine. On other hand, anyway, they eating more than turboprop engines. They consume more fuel. Well, do forgive me again that I was so long. And once again, remind you, I will send you books and I will send you couple more videos additionally. Sorry. No, you may not watch it if you don't like, because it's just, let's say, to give you information and a bit entertain you with this information together. Goodbye.